Hey guys, welcome back to the channel. And today we're gonna have another episode of breaking down algorithms, and we're gonna be talking about tries. If you haven't already, please drop a like and subscribe. Really helps me out. And without further ado, let's get started. So tries, like I mentioned in one of my previous videos. If you haven't checked it out, go look at it. It's the top algorithms you need to know for LeetCode. And what tries are, these are prefix trees that allow you to quickly test for whether or not a word exists in a set, or if a prefix of a word exists in a set. So for example, if you have like a list of a bunch of words, and at any point in time, somebody starts giving you letters and they ask you, is this part of any word within the set? So is this a prefix of any word? So if you were to actually do this naively, you would have to go through all n words in your list, and for each one check, is this word a prefix of the other word? So that can take O of mn, where m is the length of the actual target string, because you would have to do it n times once for each word, and then for each word you would have to compare each of the m letters, worst case, to see if it's a prefix. And so that's obviously not really good, especially if n is like very, very long. So with tries, what you can do is you can bring that down to O of m, where you only need to look at the letters of the target string, and you don't actually need to iterate through all the words within the list. So basically we're trading space for time complexity here, and it's pretty useful in a lot of algorithms. So today what we're going to be doing is kind of coding up this data structure and seeing how it works in action. Whenever I work with kind of these tree stuffs, I like to have kind of a try node class as well as like a try wrapper class. And the reason because it's just like having a node class makes the logic a little bit easier and it's a little bit cleaner. So we can go ahead and start by creating that class right here. So we're gonna give the try node a constructor, and all we're gonna do is it's gonna have two things. So first off, we want to be able to mark in the tree if something is the end of a word, so that way I can check if a word is in my try. And so we would have each node just like mark itself if it's the end of a word. So like if you have the word car, you'd have C at the top, A would be the child, and then R would be the children, and then you would mark R. So like we can write a couple of test cases here. So what we're gonna expect this tree to look like is, right, because you would have this, you can see there's car here, there's carrier, there's cat, and there's cats. And so you can see if someone is looking for like a prefix like carriers, they could just go through each of the carrier things and just go through this try and see if that exists in there without actually looping through every single one of the words. So you can see how the try here is a little bit helpful. And so we also want to know if something's like a word. So we would mark this R with like a star, this R here with a star, this T here with a star, and this S here with a star. And this just means like as you're traversing down, if I get to this R right here, I know, oh, car was one of my words. I know that cat was one of my words. I know that cats was one of my words. And I know that carrier was one of my words. So this is how you like distinguish and know what's a word, what's not a word. Obviously, like CARR is not part of our list, and it doesn't have a star next to it. And so the first thing we're going to create here is that boolean, and we're just going to call it like end of word. And we're just going to initially set it to false by default. Okay, and another thing we need to know is we need to have its children, right? So each node needs to be able to connect to each of its children. And one like really simple way to do that is if you have 26 letters in the alphabet, so assume we're just using lowercase letters, what you can do is just create this, like a list of nones, like this. So what this actually is it's an array of children where index I represents letter I. So now we have this like children thing, and what we're gonna do is if there's no like element there, we're just gonna do none. So obviously if you look right here for the C, there's not gonna have like a child for B or C or D, so all of those are gonna be none. Then A is just gonna be like another like node. that represents like the A node. Okay, so that pretty much does it for our try node class. And so moving on, we can just go ahead and do our try class. So once again, we're going to create a constructor here, and what we're going to have is like something like a root. Okay, so the root is just going to be a node. Okay, so now we can get ready to define some of our functions. So the first function we want to define is like an insert function. We want to be able to insert a word into our try. And so what we can do is we do this, right? We go for a letter in our word. So we loop through all the letters in our word, and we say cur equals self.root. We get the root is where we're starting at. And we want to get like the index. The index, we can get this by doing OR, so we'll just convert it to ASCII. We'll just convert it to ASCII, and we'll just subtract the ASCII value for A to 0 index it. So yeah, so this kind of gets the index within the node, and so we just have to say, so the child here does not exist. We just need to create it, and we just set our current to this. And so what this does is that for each letter, if it's not already part of your tree, you just add that to your try, and then you move your like pointer to that element. So like if I was to insert, like if I already had car and I was trying to insert cat, I would go to C, and then that exists, and now I would go to A, and then it exists, so I would try to go to T, but T doesn't exist, so I would first create the T, and then I would move to T. And so also, you notice like at the end of this loop here, I'm actually at the node at which my word ended. So what I need to also do is just say that this is the end of word, and they should insert everything into there. So just kind of like to make sure we understand what's happening here, we can actually create a print function, and it'll just take in a cur like this, and it'll take in like the word. But we're starting at the root of this try, and we're going to have a prefix currently of empty string. And so we're just going to attach each element of the try onto the thing, and then traverse down the branch, and that should give us like the overall word. So we can just loop through like the children within cur. So we'll just say for child in cur dot children, and we should get the index as well. So if the child exists, we just convert the index back to the actual letter, and we can do that by calling the char function, and what you can do is you can take in this letter ASCII value and add back the ASCII value of A, because we originally subtracted that out, and that should give you the letter. And so you can just attach this onto the word and recurse here. So you can say like self.print try, you're now at the child, adding on. Now the thing is, we need to consider like when we should actually print out the word. All we just need to check is if it's the end of word, and we print out the word. Yeah, okay, so this should work. And so yeah, we get back that carrier, car, cats, and cat are the 4 words that we were inserting into theirs. To even check this, we can even add like another one called test, just to make sure all the letters work. So yeah, this printing shows us that our try is working as expected. And so now the remaining thing to check is just like is a prefix. So the last function that we really need to look at is prefix. And so we got to pass in this word here. And so yeah, so if we want to check something as a prefix, we just have to like kind of iterate through the words. So for each letter in the word, we check. So we first define, once again, we define the current equal to self.root. So we start at the root here. And so we need the index again. And then so if we find out we don't have this child here, then obviously this is not a prefix. So that means like our try, we try to go down some branch that's not part of the try. So obviously this is not a prefix of the word. So we can just return false here. And so if you go to the very end, so now you say cur equals cur.children, just iterate down the branch. So at the very end, you would return true. So this just shows that like you were able to go all the way through the branches, so this is the prefix. Now if we want to do something even better, we can actually return the actual value here. So we can say like return null, and we can actually return the cur here. Oh, this is not Java. Return none, and then we're going to return the actual node here. And then so why this is helpful is that we can create a contains function. And so like what we can do is we can just say node equals is self dot is prefix word, and so whatever gets returned here. So obviously if not node or not node dot end of word. So if it was a none, or if it's not the end of a word, then obviously it doesn't contain this word, so you can just return false. Otherwise you return true. Yeah, we can call this a helper right here. And so right here we can just say like is prefix. We can make this a boolean thing here also, and we can just call self.helper and just return whether or not this is none. So right, so we just check that something got returned, in which case it's a prefix. So we just change this here to helper as well, and this should work exactly as desired. So yeah, so we say like let's see t print t dot is prefix. Like we can try for test, we can try test. This should be true. Something like Bob should be false. And then we can like even try contains, like test. Now we expect this to be false, but we expect this to be true. We expect like this to be true, and we expect something like this to be true, while changing it to contains would make it false. Right, so we can go through and see if this performs what we want it to do. Even better, you could do something like this. You could do like, I'm sure there's a lot of different ways to write better test cases, but if I do this here, I should expect them all to be true. So once again, see, so now we see that it's all true. So yeah, this is some pretty short code, just how try works, right? We just have a node here, and then we insert, it's kind of like DFS, you just first down the tree, and at the end you mark it as the end of the word. So yeah, that's pretty much all I have for you guys today. It's a pretty simple data structure that's pretty useful in a lot of cases. So yeah, once again, drop in the comments what you guys want to see next time. Hope you enjoyed the video, and yeah, we'll see you next week.